Hi, everybody. This is an introduction to adiabatic processes. Ooh. What is that? Well, the whole idea behind adiabatic processes is that there's a way to change the energy of a gas with something called work. Red. Work is energy added to a gas by changing volume. And what happens is that the molecules collide with the moving walls. So during compression, right, delta V is negative, something's getting smaller. And therefore work is positive, not because smaller, but because the molecules collided with a wall that was moving inward. Moving inward. So if I have like a piston, right, being pushed on some gas, right, this molecule is going to be hitting a moving wall. And therefore, it's going to leave with more energy that it came in. And because of that, the kinetic energy is going to go up. So when delta V gets smaller, or sorry, when V gets smaller, when delta V is negative, so the act of compression, I should write, it's the act of it, right, adds Ke to gas. It's the act of compression, not the fact that it's smaller. Remember, smaller increases pressure, just as a separate thing. But the act of making it smaller actually adds temperature, which is interesting. And that's completely different than there being just less space. So remember, volume goes down, pressure goes up because less space. When volume goes down, temperature goes up, and therefore also pressure goes up even more so because act of compression. These are two completely different things. These are separate mechanics, right? One of them is just PV equals nRT. Less space means more pressure, more collisions. Less space, the act of doing it adds energy, which also means more collisions. But be careful, more collisions doesn't mean more temperature. More collisions is a result of more temperature. Temperature is energy. So how is energy getting to the gas? There's two ways to do it. One, you could have heat conduction, have collisions add energy, but here you're colliding with a moving wall, as opposed to colliding with faster moving molecules on the other side of a boundary, which is heat conduction. So this is work, and expansion is the other. If delta V is positive, work is negative. They're colliding with a wall moving outward, moving away. If you collide with something moving towards you, it will add energy. If you collide with something moving away from you, it's going to take energy away from you. So if you have a ball hit a wall that's moving away, it'll actually, the ball will lose energy, and the little balls of the molecules, we're assuming molecules are little balls They aren't, but the kinetic theory of gases assumes they are. A good enough assumption, it works pretty well. Then we get that it loses energy during expansion. So here's the box notes like this. And now we have a formula for it too. Work is negative P delta V. So the negative sign confirms the concept that we said here, and it depends on the pressure pushing over a change in volume. Newton per square meter times cubic meter is a Newton meter, which is a joule. So indeed, pressure times change in volume gives you energy. Easy done. So now we want to go through the different processes, right? Oh, sorry, a name first. If you have an adiabatic process, so there's isobaric, isothermal, isochoric, and now adiabatic, that is when there is no heat, so only work is changing energy. Just work. So you're squeezing something or expanding something adiabatically. So to have no heat transfer, it needs to be insulated. Or very fast. So there's no time for heat conduction to occur. So if I squeeze something, right, the pressure goes up and the temperature goes up, which actually makes the pressure go up even higher. So the pressure goes doubly up for volume being lower and temperature being higher. So it's not iso anything. If volume goes up, then the pressure goes down doubly because the temperature goes down and there's more space. There's more space. The collisions with the moving, expanding wall cooled it down, less energy. Here, if we compress it, there's more energy. Please let this make sense. We're going to go through this in detail in the next couple of days, but this is just the intro of let this bubble make sense. This is an adiabatic process. Nothing is constant. Everything is changing because there's only work is changing the energy. Everything can change somewhat organically just by the collisions with the wall adding energy. So let's do an example of an isobaric process, right? Let's do isobaric heating. Let's go from 300 Kelvin to 600 Kelvin. Let's do the example that was in the hot pink homework. 200 milliliters. And so this is now we do have a heat source. So now we have like some container that's being heated. That's expandable. So we have positive Q going in, and the delta P pressure gradient is going to expand it outward isobarically. Obviously, as it expands, the pressure drops and equalizes. Right, this is all in your notes. You should be familiar with this. Please know this. We're not forgetting this. We're bringing it back, and we're going to calculate the heat and work done now. So what is Q? What is work? And what is delta E total? This is the one we're going to focus on right now. Make it pink. Work is negative P delta V. And we want the pressure to be 1 atm. Well, first we need to plug it in the pressure, 101,325 in pascals, not atms. And we want delta V. Delta V is final minus initial. So what is the final pressure? Well, the final pressure we know we can get from the ratio. It's an isobaric. So V1 over T1 equals V2 over T2, or the fact that the temperature doubled means the volume doubled at constant pressure. This is isobaric processes. This is what we're supposed to know already, right? Let's not forget it. So this should be familiar, or at least ring a bell, right? So this is what we're doing. So V2 is 400 milliliters, which means that delta V is what? Well, it went up. So it went positive 200 milliliters, which is positive 0.0002 cubic meters, because we divide by a million to convert to cubic meters. So that's what this is right here. And I get, right, that delta V is positive. Pressure, of course, is positive. So I get a negative value of negative 20.265 joules of work done. So what's interesting is that if you remember, so say I heat something up, the work is negative, and I allow it to expand. It expands because of pressure gradient, right? But in doing so, it actually loses energy. So it takes, this has to overcome the delta V positive, work is negative. It has to overcome the energy loss to pushing the balloon out. Does it take energy to expand something? Yes, it does. So this heat actually has to not only heat up the gas, but it has to expand the balloon as well, or expand the container as well. So it actually has to do two things. So I have my heat source here, right? Heat source, whatever it may be, hot plate, a fire, something like that, just something that's hot, hotter than this. It has to overcome both. So how do we do this? How do we actually know what is Q, what is W, what is delta E total? So delta E total, as you remember, is 5/2 nR delta T for air. Work is negative P delta V, right? So where does Q come in? Well, the point is there's two ways to heat up a gas, or to increase the energy of a gas is the better way of saying it. There's heat and work. And this ends up being now the set of equations we want. This is the first law of thermodynamics right here. The first law of thermodynamics says the change in energy of a gas is the heat plus the work. There's only two ways to do it. And obviously, if you have one that's negative, one that's positive, they'll just add up. And one will add, one will take away, or both will add, or both will take away, or one won't exist, one will exist. We could have adiabatic, isochoric, isobaric. We can have all these things, but no matter what process you're doing, there's only two ways to increase the energy of a gas: heat and work. First law of thermodynamics. Here's our equations, everybody. So you might notice that this goes here, and we can then from that solve for Q. So this is how we solve for Q. There is no formula for Q, although we can prove MC delta T from this. If you had that in a chemistry class, we can prove that. We can derive the specific heat C from this equation, but it comes from this equation. This is the equation for heat. It's just another source of delta E total. So in our isobaric process here, where we had V1 equals 200 milliliters, V2 is 400 milliliters, which we solved for. T1 is 300 Kelvin, T2 is 600 Kelvin at a constant 1 atm. We can solve for delta E total equaling 5/2 nR delta T. N turns out to be, I think 0.008 something. This was on our homework. And you plug that in there, you get this from PV equals nRT. P1 V1 equals nRT1. You just plug in V1 and T1 and 1 atm. Well, convert to pascals and cubic meters, and you can solve for N. Plug that in there, and we get positive 50.66 joules. There you go. Right? So the point is that delta T is positive. I should write T increases. You shouldn't write delta T increases. Sorry, I got to be better at that myself. delta T is positive, which means T increases, same thing. Because Q overcame W. Positive Q overcame the negative W. So we can use the first law of thermodynamics to solve for Q. Remember, work is negative because expansion. And we have delta E total equaling Q plus W. So this thing goes in there. The work of negative 20 point, what was it again? 265 goes here. And we get that 50.66. Please, guys, be careful, positives and negatives. 265. So I add 20.265 to both sides. And indeed, Q is a much more positive number, which is positive 70.925 joules. So the heat had to cause the expansion, because ultimately, because expansion due to pressure gradient due to heat. So ultimately, the heat caused the pressure gradient, which causes the expansion, which takes energy away. So the heat actually had to be responsible for two things, didn't it? The heat was the source of the pressure gradient, of the negative work, or overcoming the negative work, and it was responsible for increasing the temperature of the gas. So this increased T and increased V, did both. And recognizing that it did both is really important. Okay, two more. Isochoric, and I'll save adiabatic for another day. Isochoric, if I have a 200 milliliter at T1 equals 300 Kelvin, and I increase it to 600 Kelvin, what is the work done? What is the delta E total? And what is the heat? For isochoric, what is the change in volume? 0. It's so easy. So that means the work done is 0 for all isochoric processes. That is so good. And therefore, the change in E total is just from heat, which is nice. So that means, and in this example, we had delta E total equals 5 halves NR delta T, where the delta T was positive 300 Kelvin, N was like 0.008, something. And we had positive 50.66 joules. This was from the homework, by the way. So that means Q equals positive 50.66 joules because work is 0. So this one's easy. Isochoric is so easy, where the heat is the energy. So in an isochoric process, there is no work done, so the only energy exchange is from heat conduction. That's it. And now just a little concept with isothermal. I won't do the math yet. So if I compress, if I do an isothermal compression, right, what happens is my piston goes down, right? And as we noticed, that lower volume increases the pressure at constant T. But we just said that lower volume adds energy. There's positive work being done, which means that we have to have a negative value of Q. That heat must be lost, so it has to be non-insulated. And the reason it has to be non-insulated, I hope, is obvious. Because if I did insulate it, I would get the fire piston. If I did insulate it, I would squeeze it and it would heat up, it would warm up, right? So I have a positive value for Q. I'm sorry, a positive value for W and a negative value for Q in compression. So Q is negative to maintain T. And in both of these, delta E total is 0, of course, because it's isothermal. We've covered that, which means Q equals W, or Q equals negative W. The absolute values equal each other, but Q is negative when W is positive. And of course, with expansion, we'd have the opposite. If I pull upward, V increases, makes P decrease, which is not the mechanics of heat, right? That's just the result of isothermal, right? P1V1 equals P2V2 is the result. But how does T stay constant if we're doing negative work? Well, this removes energy, which then is replaced by heat conduction from the room. So Q is positive to maintain temperature. It's supposed to say maintain. And then we can draw here. I have a negative Q due to negative W, sorry, due to expansion, which makes Q positive to maintain it. And those are just the opposite of each other. So when work is negative, Q is positive for an isothermal. This is isothermal, by the way. And it therefore cannot be insulated for, otherwise it would be like an ice piston or a fire piston. It would be cooling or expanding, cooling and expanding, heating or warming for compression. But what happens is the heat regulates, so the room manifests Q, positive or negative, to maintain T. So when we say it equalizes with the room, that means you have to allow to equalize with the room's temperature. You have to allow heat conduction. Boom. So Q is never 0 in an isothermal process. We did it. Sounds good to me. Have a great day. See you in class.